Imagine this. It's November 2014, and astronomers detect a massive burst of X-rays from the center of a galaxy 290 million light years away. They thought it was a supernova, but they were wrong. This was something far more dramatic. A star, just like our sun, wandered too close to a supermassive black hole and was torn to shreds. The black hole literally fed on the star. And yes, fed is the actual term astrophysicists use. Events like this, called tidal disruption events, are incredibly rare, happening maybe once every 10,000 years in a galaxy. As the star got close, the black hole's gravity pulled harder on the near side than the far side, ripping it apart in a cosmic spectacle. This stellar spaghetti spiraled into the black hole, forming a glowing hot accretion disk. This disk blazed with light, UV rays and X-rays, making it visible all the way here on Earth. What's amazing is that this event essentially switched on a dormant black hole, one that wasn't actively feeding, allowing us to study it. Now, you might be thinking, that's a cool story, but how do we know that's what really happened? Are scientists just making this up? Well, hold that thought, because things were about to get even weirder. For years, after the initial flare, scientists pointed 3 different X-ray telescopes at this spot in the sky. What they discovered was astonishing: a strong, steady pulse of X-rays, brightening and dimming every 131 seconds. This pulse was consistent across all 3 telescopes over 450 days. It didn't get weaker. In fact, the pulse became even more prominent over time. So, what was causing this cosmic heartbeat, and what could it tell us about the black hole itself? To understand that, we need to talk about what makes a black hole a black hole. They're surprisingly simple objects, defined by just 2 main properties: mass and spin. We can forget about charge for now. Mass is pretty straightforward to figure out. By observing how a black hole's gravity affects nearby stars and gas, we can calculate its mass. And we've found them ranging from a few times the mass of our sun to billions of times more massive. It's widely accepted that nearly every galaxy, including our own Milky Way, has a supermassive black hole at its core. But what about spin? That's a much trickier beast to measure. Since black holes are born from collapsing stars, and all stars rotate, it's a safe bet that all black holes spin. When matter falls in, it adds its own angular momentum, kind of like a figure skater pulling in their arms to spin faster. Black holes can spin incredibly fast. The problem is, a black hole's spin only really affects things that get very, very close to it. To measure spin, we need to understand a concept from Einstein's general relativity called the ISCO, or the innermost stable circular orbit. In high school physics, you can orbit a planet at any distance, but near a black hole, there's a point of no return. The ISCO is the minimum distance where a stable orbit is possible. Any closer, and you're doomed to fall in. For a feeding black hole, the inner edge of its glowing accretion disk is located right at the ISCO. And here, that's the key. The size of the ISCO depends directly on the black hole's spin. The faster it spins, the smaller the ISCO gets, allowing matter to orbit much closer. The spin is measured on a scale from 0 for no spin to 1 for the maximum possible spin. As the spin approaches 1, the ISCO can shrink by a factor of 6, getting tantalizingly close to the event horizon itself. So if we can measure the ISCO, we can calculate the spin. How do we do that? One way is to analyze the light from the accretion disk to infer its size. Another method uses X-rays from iron atoms swirling near the black hole. The extreme gravity and speed stretch and distort the light in a specific way that tells us how close the iron is to the black hole and therefore the location of the ISCO. But for this particular event, astronomers used a third method, those mysterious 131-second pulses. Those flashes had to be coming from something orbiting incredibly close to the black hole, right at the edge of the ISCO, moving at a significant fraction of the speed of light. The team studying this came up with a fascinating theory. They proposed that before the star was torn apart, there was already a white dwarf star in a quiet, stable orbit around the supermassive black hole, completely invisible to us. When the new star was shredded, its debris formed the accretion disk, which then engulfed the white dwarf. This created a persistent hotspot of glowing matter on the white dwarf's surface, which we see as a pulse every time it orbits the black hole. This tiny, orbiting hotspot acts like a celestial stopwatch. Its 131-second period allowed scientists to directly calculate the orbital distance, and from there, the black hole's spin. And the result was staggering. The black hole is spinning at least 70% of its maximum possible speed, and maybe even as high as 99.8%. This means matter at the inner edge of the disk is whipping around at over half the speed of light. This was the very first time a black hole's spin had ever been measured using a tidal disruption event. And the implications are huge. The vast majority of supermassive black holes, maybe 95% of them, are dormant and impossible to study. But when one of them shreds a star, it lights up and gives us a rare opportunity to measure its spin. Why does spin matter so much? Because it's a fossil record of the black hole's history. If a black hole grows mostly by smoothly accreting gas and dust from its galaxy, it should spin very fast. But if it grows by chaotically merging with other black holes, which come in from all different angles, its spin would be much lower. By measuring the spins of more and more black holes across the universe, we can start to piece together the story of how they, and their host galaxies, grew and evolved over billions of years. Each time a star meets its fiery end, it shines a light on one of the deepest mysteries of the cosmos. Thanks so much for watching. If you found this journey to the edge of a black hole as fascinating as I did, be sure to hit that like button and subscribe for more deep dives into the universe. See you next time.